Let me remind you that we are recording this, so if you don't want to appear in the video, that's the good time to turn off your camera. So the first speaker is Griffin Hosseinzadeh. I hope I pronounced correctly. So he's currently postdoctoral researcher at the University of Arizona Stewart Observatory. He got his PhD at UC Santa Barbara in 2018, and he was subsequently postdoc at the CFA working with Professor Ido Berger. So his research focuses on using observations of many types of explosive transients to answer questions about stellar evolution. And he also works on gravitational wave follow-up and machine learning applications in the time domain astronomy. Let me just remind you that we still have plenty of space for the one-on-one appointment, so you are more than welcome to take advantage of this. So the talk of today is titled A Tale of Two Supernovae, and with that, the floor is yours.
Thanks very much. Hi, everyone. It's great to be back. This is completely not the title that I put in the email, but this fit on the slide better, so I put it in here. What I'm going to talk to you about today is young supernovae. I'm going to not talk over this, actually. Just enjoy this animation of a supernova. This is from some paper where they observed it with Kepler. It was really cool. And notice also the time scale down here. It's hard to read the numbers, but this is 1 hour, 2 hours. So the point I want to make with this animation is you went from looking at a star, something that really looks like a star, there's a surface there, to something that looks like an expanding cloud of ejecta in just a matter of like 2 hours, right? So when we are studying supernovae as a probe of stellar evolution, what we'd like to do is observe a supernova and connect it back to the star that exploded. One of the best ways to do that is to observe it very, very early on when the observables are still connected to like the initial conditions. In other words, the intuitive way of thinking about it is there was some point there where it still looked like a star for a little bit after it exploded. And if you can observe it during that time, that's how you can really get strong constraints on what the star was before it exploded. And just a reminder for those of you that are not in the field of supernovae, which is probably most of you, we almost never actually observe the star directly before it explodes. That is only possible in the Milky Way, where there hasn't been a supernova for centuries, or in the very nearest galaxies where we happen to have HST images from before the supernova went off. So the only way to really connect the most supernovae back to their progenitor stars is by observing the supernova observables themselves, not the actual star. And in particular, we're probing the last stages of a star's life by using supernovae, just whatever it was doing in the months or years before explosion. And those are phases just because of a timescale argument. We almost never observe those phases in anything in the Milky Way where we can get good data. So again, this is really a unique way of observing stars to understand these least understood parts of stellar evolution. So maybe I've convinced you that we should do this. The question is how. It's not easy. The issue is that you really, in order to catch something within a day or so of explosion, you have to just be looking all the time. You can't be waiting for it to go off and just happen to find it. So at Arizona, we're running a survey called DLT40, which it's a great name, stands for distance less than 40 megaparsecs. We just look at all of the galaxies within 40 megaparsecs of us every 12 to 24 hours. Just use a small telescope. These prompt telescopes are like 0.5 meter. In Chile, we have one now in Australia also, and one in Canada. So in the Northern Hemisphere, we get daily cadence. In the Southern Hemisphere, we get 12-hour cadence. And the idea is, if you just observe things within 40 megaparsecs, this is the distance with a small telescope that you can really see things right after they explode. So this is just like a limiting magnitude diagram here, the black line. You can see a typical type 1a supernova within the first day or two after explosion is that blue line. And this dotted line where those blue and black lines intersect that's basically the motivation for why we picked DLT-40 instead of DLT-50 or DLT-100. It's just things where you can observe them within a day of explosion with a half-meter telescope. And these are cheap, easy to get time on, robotic. So that's why you want to use a small telescope like that. So we discover typically one supernova a month or so, one every 2 months, depends on weather and things like that. It's not a lot of supernovae compared to big surveys out there like ZTF, but it is, each one of those is going to be interesting. It's worth writing a paper on just by itself because there are so few supernovae observed this early when they're down at -14th magnitude. So then after we discover these, we want to start getting spectra immediately because obviously spectra give you much more information than just a single image in an unfiltered telescope like the survey is. So we partner with Las Cumbres Observatory, which many of you are familiar with. It has telescopes all over the world in both hemispheres and distributed in longitude. And they're all robotic and easily controlled over the internet. So we can just, whenever we discover a supernova, immediately click a button and get a spectrum scheduled of that supernova within the next 12 to 24 hours. And I want to also give a shout out to SOAR, which I've been using a lot recently, which they've created this Eon mode where they are also Q schedulable now for some nights of the year. I wish it would be all nights, but other people would disagree with me. But anyway, whenever it is on the telescope, we've been doing a lot of classifications. It's great to have a Q schedulable 4-meter telescope. So we can usually get a spectrum within a day and start getting really high cadence every 6 to 8 hour photometry using these facilities. And of course, because I'm in the high energy seminar, I have to go as high energy as possible. We also will always submit a Swift TOO request to get UV photometry of these sources, very high cadence starting very early, because at these early times, the SED just peaks in the UV, and it's very interesting to see where that is. Look at the water over here. So with that motivation, I'm going to talk about 2 case studies today, recent papers that I published. Yeah.
Just a question on the Progenitor. What fraction of things that you trigger on actually end up being supernova? Like, if you just discover
almost all of them are supernovae. The only main contaminant is sometimes we'll get supernova imposters, as they're called, which are just like outbursts of LBV stars, which can get up to -14th magnitude sometimes, but then they fade immediately. So then you'll know. But yeah, just in that magnitude range, there's not much else except young supernovae. So I'm going to talk about 2 supernovae today. One is a type 2, which is a red supergiant exploding. And this can teach us a lot about the last stages of mass loss in red supergiants in particular and massive stars in general. And I'm also going to talk about a type 1a supernova, which is a white dwarf explosion. Getting that very early data can tell you about what is the nature of the binary companion in that system of the progenitor, and how does the white dwarf actually ignite and explode. So I'll start with red supergiants. This is technically not the correct scale, but this is the picture you should still have in your head of a red supergiant, Betelgeuse, of course, our favorite. And we're finding recently that they're not just sitting there doing nothing for the last years of their lives. There's a lot of material around these stars. And we don't really understand exactly how it gets there, if it is a steady wind or eruptive mass loss or what. And when that star explodes, it's going to then run into all of that material. And that's one way that we can actually probe the location, density, composition of that material. So getting at red supergiants this way gives us access to many more than we could observe just in the Milky Way, because we have access to all of the rest of the galaxies in the universe. And also it gives us access to the latest stages of evolution, as I mentioned before, where you can see what the red supergiant was doing in its last year, which we almost never see in the Milky Way. So what does this look like in practice? One of my favorite plots from a paper ever. This is a time series of spectra over the first 12 hours of a supernova. The continuum is subtracted here, so we're just showing the emission lines. But you see there's these very unique electron scattering profiles, very narrow emission lines. And you see there's some very high ionization elements here, like nitrogen 5, oxygen 6, oxygen 4, and helium 2, which only happen at very, very high energies. This is what we sometimes call flash spectroscopy, which is because the shock breaks out of the surface of the star, and either that radiation itself or the very hot ejecta that has just been broken out of will ionize this material to a very high state, and it will recombine over just a few days. So if you don't observe this within 3 days or something like that, you will not see this. But this is a signature of that material that's outside of the star before it exploded. And so you have to observe it within, let's say, 5 days conservatively. And you can use these observations to really map out what is the density profile of material around that star. So for example, here, this is from the same paper as the data I just showed. You can get a constraint on the density of material up here at very close into the star, which you would not see if you observed it later on. You can see the upper axis here, days since explosion, corresponds to the radius that you're probing outside of the progenitor star. So if you only observed it 5 days after explosion, you would likely not see anything and not know if there is any wind here. But if you observe it within these first few days, you see there actually is a dense nearby CSM, circumstellar material. I didn't say it, sorry, CSM. There's another clue, which is that if you look at the early light curves, they tend to have kind of a peak just a few days after explosion. You see in all the filters, there is kind of a peak here before settling onto the plateau, which is typical of this type of supernova. And by modeling these light curves with some radiation hydrodynamic code, you can get, you can also get constraints on the density and radius of that material.
Off doesn't work again.
It's okay. It may turn off again in like 10 minutes, like it did last
No.
I'm not too worried about this if everybody can still see. It's not the greatest contrast, but it's okay.
Sorry.
That's okay.
Let's
It's
try
fine.
magically can turn off again.
Yeah. So as I was saying here, the solid lines are a model that includes some wind around the red supergiant before exploding. The dashed lines are if you don't have that wind, and you can see that in almost all the filters, the wind model, the fit with wind, the solid lines fits much better. So you can use that to get constraints on the nature of that material. So coming to the supernova that I worked on recently, we discovered this supernova probably within 6 hours of explosion were the first observations. I'll go through the quick story for you. Actually was discovered not by us, but by the Atlas survey, which is another supernova survey that's going on, and nearby objects and all that stuff. We had an observation with DLT-40 just a couple of hours before that. They just happened to notice it first. A little bit embarrassing. Our computer was broken, that's our excuse. And we also had a very stringent limit the day before to say that there was no supernova there. But the most amazing part of the story actually is these points down here, which were taken, this is in a very nearby galaxy, and these are the kind of galaxies that school children like to observe with Les Gumber's observatory. So there just happened to be images of this galaxy at like probably 6 hours after explosion. We don't know exactly when the explosion was, but this is actually the most constraining way to find out. And there is a supernova detected in those images. So we use those too, and by fitting a curve to those 3 points, you can get a pretty good constraint on when the explosion was. So there's some, the moral of the story here is make sure that you give time for education and public outreach on your telescopes, because it may pay off for you. So then, of course, we got a spectrum as soon as possible, about a day after we discovered it. So that's about 2 days after explosion. I should use my pointer. So the black lines are this supernova here, 21YJA. This blue spectrum is actually one of the ones that I showed you in that initial spectrum of 2013 FS, showing that time series of spectra. And other ones, these are other spectra of type 2 supernovae at similar phases. You can see in the other supernovae, there are these very narrow emission lines, as I mentioned, of nitrogen-3, carbon-3, helium-2, which indicate some CSM that's being illuminated by the supernova shock. In our supernova, there aren't very narrow lines like that, which is interesting because I was beginning to think that all red supergiants had CSM around them. But instead we have this very weird lead-shaped feature. I didn't make up this term, sorry, but this is what's in literature. You can see the green curve here is kind of not the same shape as like a typical P Cygni profile, which is, you can see here in H alpha and helium-1. And it's a question of how do you produce this line profile? Is it a combination of all of those narrow lines adding together, or is it something stranger? So one possibility is that it's just weak circumstellar interaction. It's all of those narrow lines added together, very low intensity, and you get some kind of more spread out thing. Another option is modeled by Luc Dessart in one of his recent papers, where you, instead of having kind of a question of what is the boundary between CSM and the envelope of a red supergiant, but instead of having CSM, you have just like a extended envelope on your red supergiant. And if the lines form in that low density extended envelope, he actually does get some line profiles that look like that. For example, look at this blue model spectrum right below my black spectrum here. It's hard to see, but there is this kind of same line profile shape where the peak, it could be in this case helium-2, which is blue shifted and much broader. Maybe not as broad as in our observed spectrum, but that's just a question of velocities potentially. So maybe it is possible to get this without CSM if you have some kind of strange behavior in the red supergiant before explosion, which many people study what red supergiants are doing in that situation, but hasn't really been directly observed. So coming back to the question of what kind of star was this that exploded, if you look at the light curves, you can also see that the plateau is almost 120 something days long, which is very long for this type of supernova. I don't expect you to know that, but just take my word for it. And from the fall from the plateau, the nickel tail here, which is powered by radioactive material that's produced in the explosion, you can get a mass of nickel, radioactive nickel, which is produced. And that mass is very, very high for a typical type 2 supernova. So both of these are giving us clues that the progenitor is probably a very massive red supergiant, like at the high end of what is still a red supergiant. Daichi is a super expert in this. He's in the audience up there. So go talk to him about it later. But we also had HST images of this field from way before explosion in 1997. So we have the option of actually directly searching for the red supergiant progenitor in these images. Beautiful galaxy as usual. This is where the supernova happened in the galaxy, and these are cutouts in, here's the HST image, and we have other archival images which are not as deep. So this is the most constraining one here. Within the uncertainty of the position, which is that red circle, there is nothing there to pretty deep limits. So, okay, if it's a massive red supergiant, it should be there. And so if you put this on an HR diagram, this is the crazy twist in the story, you can exclude almost all of the high mass red supergiants, which is this whole gray shaded region, compared to these single star evolution plots, tracks in black. So the limit here is something like, has to be less than 9 solar masses. Of course, the lower limit of things that explode being like 8 solar masses. So this is a very strict constraint, which is totally in conflict with all the other observables of the supernova. Something very interesting. So where does that leave us? The red supergiant could be variable in time, so that in 1997 it was faint, and but it was still a massive red supergiant before it exploded. I mean, okay, the mass is not varying that much, but it was doing something that obscured it beforehand. We know red supergiants do some weird stuff, but in order to account for this discrepancy that we see, this would have to be like one of the most extreme ones ever, like Betelgeuse level, which we know is not common.
How much more dust than Betelgeuse would do?
So here's how much dust. The other option is that there's dust out there. And if you take a reasonable wind parameters, 20 kilometers per second, 10 to the minus 6 solar masses per year of mass loss, you can only extinguish this by like tenth of a magnitude, right? So this is like totally not even close to explaining the discrepancy. So then that leaves us with the last option of those single star evolution tracks that we're comparing to are not describing what the progenitor was doing. But then that's weird because it has to be, you would have to have interaction be extending the, changing the behavior of the star in the HR diagram, but still have a big hydrogen envelope left on your star. So it has to not really be interacting strongly. So that doesn't really make sense either. So it's still somewhat of a mystery. And I'll come back at the end of the talk to talk about like what we could do potentially to change this. I think there's some problems. But this is just, I think what it shows is that we need to explore this parameter space more. So this is only one example, but we should be getting dozens of examples, all different parameter space of mass loss and progenitor mass, that we can understand this better. So let me move quickly, this one is much shorter, to the type 1a supernova that I recently studied. So these are exploding white dwarfs. We know they're a white dwarf exploding, and we know they're in a binary system, but we don't know what the companion star is. Could either be another white dwarf, which we call the double degenerate scenario, or it could be either a main sequence or giant star, which is accreting material onto the white dwarf, which eventually will cause it to explode. And in addition to that, we also don't know how the white dwarf actually explodes. There are many mechanisms proposed about how do you get to the ignition point, and how does that actually unbind the star. I won't go into the details of that, but these are kind of two separate but related questions in type 1a supernovae, which we use all the time for cosmology, but we actually don't understand very well. So one way of getting at this binary companion question is you could potentially actually see the explosion run into that binary companion star. Dan Kaysen predicted this in 2010. Here's a little diagram of what that would look like. You could see that you cut out, if you have a favorable viewing angle, you can see that the ejecta are shocked by this progenitor, this companion that it runs into, and the ejecta will glow a little bit. They'll be heated up beyond what it already was. And so you'll get light curves that look like this, which depends on the solid angle occupied by the binary companion, but you basically get a bump in the very early light curve, which is stronger in UV and bluer bands, and then weaker in optical bands. Nobody ever sees anything like the green lines there, but we do see things like the blue and red lines potentially. The problem is there are also other things that can cause bumps in the early light curve, and just because we haven't explored this parameter space very long, it's hard to tell what the quote unquote normal behavior is if there's no binary companion there. So for example, some types of explosions, if there's a helium shell that ignites first, if you have a pretty low mass white dwarf, which are these bottom lines, you can see that they give a little bump in the first few days. Also, if you have a some weird distribution of nickel, radioactive nickel in your ejecta, then you can get bumps early on. This is a very fine-tuned model, so I totally believe that this is something that happens in nature, but it is possible. If you put a clump of nickel way outside of everything else, that gives out a lot of light before the main supernova becomes bright. So I was looking back, actually, when I was at the CFA for 1 month, my first postdoc symposium, I gave a talk about this supernova, for which we had very early observations. This was discovered by DLT40. We got this 6-hour cadence over the first 5 days in multiple wavelengths. And this is one of the most amazing data sets on type 1a supernova available. And now I'm here 3 years later talking about a new supernova, which has 2-hour cadence over the first 5 days, and multiple bands, including the swift bands at sub-daily cadence for the first 5 days. So this is really the kind of data set we need to constrain these models, because you can see they're pretty similar at early times. And trying to model the behavior in detail is the only way that we'll be able to differentiate them at multiple wavelengths. That's very important. So unfortunately, again, I have bad news for you that the data don't totally fit the models. We fit all 3 of these things that I mentioned, colliding with the companion star, which is on the left here, and these other 2 models, the helium shell and the nickel shell on the right-hand side. You can see in all cases, the bump is too strong in the UV, which is interesting. And it's also difficult to simultaneously match the color during the bump and at the peak of the supernova. So there's something that we don't understand here about in the models when they're confronted with this really high quality data. So other clues, if we look at the spectra of this supernova, the earliest spectrum, which was like 17 days before peak, that's the purple one here, the darkest purple one, show this very strong carbon-2 feature, which is a signature of, carbon is present in the progenitor. It's a carbon-oxygen white dwarf. So if there's carbon left after the explosion, that's not predicted by some models. Some models think it should burn completely. So unburned carbon in the ejecta can put some constraints on which models are viable, but it still doesn't totally constrain it to only one. This is also like most likely, I don't know, don't quote me on this, probably the earliest type 1a spectrum ever taken. So there's a student in one of our collaborators group that's gonna write a paper just on that spectrum, essentially. Very interesting stuff. We also have a radio non-detection around, in the early light curve of the supernova, which constrains the mass loss rate. Not the strictest constraint ever, but it's like in the top 5 or so, saying that there's no material in the environment as there would be if there were a non-degenerate companion star. And of course, one of the ones that always messes everybody up is that there's then going to be a nebular spectrum later on to see if there's hydrogen emission, which could only come from a non-degenerate companion at very late times. We're just now able to observe it again. So this hasn't been taken and analyzed yet, but keep your eye out for it. So to bring this together, both of these supernovae benefited from very, very early data, but unfortunately, in neither case did we have models that totally fit every part of our observations. So in the case of the type 1a supernova, we don't understand what the underlying explosion looks like at these days 0 through 5 or so. And therefore we can't understand if there should be if we're seeing a bump on top of that or not, or if the bump is just part of the 1a. And going back to the type 2 supernova, we don't fully understand how to translate the full phase space of circumstellar material and red supergiant mass loss into the observables, both in the spectra and the light curves of type 2 supernovae. So in both cases, I'm calling on all of our supernova theorists to please care about the details here. You can't just assume that a type 1a supernova is a black body, because it's not. That's one example. And we really need models that are able to deal with this very high cadence early data that we can now get on a pretty regular basis. So thanks for listening. Happy to take questions now, or I'm around for the rest of the week and happy to come talk to you. Thanks.
I'm sorry for the bad lighting here.
That's okay.
Okay, so do we have any questions from the in-person audience?
So I was just wondering, if there are issues with dust, I didn't see any photometry in, say, the near infrared J and K bands. Would that help untangle this?
So you're talking about the progenitor, images of the progenitor in those.
Well, your photometry, all this photometry.
Yeah. So, okay. So for the photometry, we have, not very much in the infrared. We have Z and we have 1 point in J and H. I think we can say from the observables, especially the very early blue spectrum, that there's not a lot of dust, in the line of sight. That doesn't mean there wasn't dust around the progenitor that got destroyed in the explosion, which is what you would need. But we unfortunately are just restricted to the single band of HST imaging that happened to be present in the archival images. We don't have, we can't go back in time and take those images. Yeah.
Speaking of going back in time, it seems like, how many galaxies are there within 40 megaparsecs? And, is there a good reason to go with HST and just make sure you get deep precursor images? Yeah,
I don't know off the top of my head the number, but there have for sure been HST proposals to do that. And it's true, I don't know if any of them have been approved as like a snapshot proposal to specifically just image those galaxies. But it's true that over the course of HST's lifetime, this sample is actually growing where there are images in the archive. So this is possible more and more. It used to be that there were like 5, and now there's like dozens. And there are even some in there sitting there that somebody should just analyze that. It just hasn't been done yet.
Yeah, I'm also wondering about this object. What about models where the star is massive enough that it loses most of its envelope at the end of the main sequence from when?
Yeah, the issue there is that the supernova itself shows strong hydrogen lines. So there needs to be a big envelope there in order to reproduce the spectrum. And the fact that this long 100-day plateau requires that there be a lot of hydrogen there. So it can't lose very much of the envelope in that case.
What was the earliest spectrum post supernova? What was the time lapse for the first spectrum?
The one that I just showed there?
Yeah.
It was 17 days before peak. We don't have very strong constraints on the explosion for that one.
Didn't you have to do them half a day? Or
That was the in this case, no, we didn't. That was the other supernova that I had it very strongly constrained. But you know, if we compare it to light curves of other type 1a supernovae, depends if you're correcting for stretch or not and all that. But this is probably like within a couple of days of explosion, if not less than 1.
I don't see other question from you. Amy, Juana, do you see any question online?
I don't see any hands raised or anything in the chat.
Okay, so let's thank Griffin again. Thank you so much. The light is helping us now. So let me introduce the second speaker. I don't know her, so I don't know if she's here. Okay. We have the presentation on the computer. Do we have the animation in the presentation? The animation is in the presentation or not?
It's actually not, but
No?
I guess I can reload it.
We can try, but we can try to use your computer. But
Yeah, sure.
no. Okay. What about we don't?
Oh, do you have like something to attach?
Can we have you not use the animation while you're in program?
That's okay. It's okay. I guess I can use that.
Okay, so let me introduce the second speaker. So she's from here. She's Priyanka Chakraborty. She got her PhD at the University of Kentucky, working with Dr. Gary Ferland. And she's currently working in the Atom DB group with Dr. Adam Foster Randall since December 2021. The title of the talk is Exploring X-ray Universe in the Microcalorimeter Era with Claudi. Thank you so much, and the floor is yours.
Hello, everyone. Thank you for being here today. So today I'm going to talk about the dissertation project I worked at the University of Kentucky. The title of the talk is also the title of my dissertation, Exploring the X-ray Universe in the Microcalorimeter Era with Claudi. So let me start by discussing the motivation behind this work. So in the next few years or decades, we are going to have a lot of high quality spectra, thanks to the microcalorimeter missions planned PRISM and Athena. So if we want to understand the detailed spectral features that will be visible to us, so we need a complete understanding of the underlying atomic physics and how the line form. We also need to understand the atomic processes in collisionally ionized and photoionized astrophysical plasma. And we need to develop general tools that can be applied for systems with a broad range of column density or a broad range of astrophysical sources. So in this work, I have used Claudi for all my simulations. Historically, Claudi included X-ray, but it was not designed to do high resolution X-ray analysis. So there are some updates that I did to Claudi, and also I'm going to discuss about some of the atomic processes that we use to understand the high resolution spectra, and I'll show you application on heating observations and Chandra GTT spectrum. So the plot that you see here is a very famous plot observed by Hitomi of Perseus cluster It's also their poster child, and a lot of my work went into understanding the behavior of these lines. So we have 4 published papers in ABJ based on this work. And we also have a research note that describes one of the important updates to Cloudy. There are some other updates that I did also, but because of lack of time, I couldn't include it. So this is one of the important one I'm showing you here, but if you're interested, we can talk about it later. So the plot you're seeing here is on the update in the K alpha energies in helium-like ions, hydrogen-like ions. So this is the difference between cloudy and mist K alpha energies, and then it's plotted with the K alpha energies here, and also like on the top, I have shown the atomic numbers there. So the green circles that you see here, they are the old cloudy minus mist energy difference, which is I have also compared it with the current and future X-ray observatories. There is GRISM and Athena and Chandra XMM Newton. So as you can see, after sulfur, for all the elements, the old energy difference is kind of bigger than Athena and GRISM accuracy. So it was not compatible for the microcalorimeter observations. So after updating the energies, we get this the red triangles that are now, they are almost 15 to 3,000 times better than the old ones, and they are now smaller than the accuracies of this instrument. So now these energies will be now compatible for the microcalorimeter observations. So there are 4 different line formation conditions in a cloud. They are called cases A, B, C, and D. And depending on whether the cloud is collisionally ionized or photoionized, we can assign these line formation condition. It also depends on their optical thickness. So on the top, I had a nice animation there showing the collisional ionization process, but a collisional excitation process rather, but unfortunately it doesn't work here. So on the diagram here, I have shown case A and case B. On the left, there is case A for optically thin cloud. So here, all the Lyman lines that are emitted will be escaping the cloud without any sort of interaction. On the right, this is called case B, where the cloud is optically thick, and the higher order Lyman lines will undergo multiple scatterings, and they will be converted to Balmer alpha and Lyman alpha, or if it's higher order, other Balmer lines. So there will be a redistribution in the line intensities because of this kind of interaction. And here I have shown cases C and D for photoionized cloud. So as you can see here, the lines are being formed by recombination, but also they are being enhanced by continuum pumping, which is if a photon is there with appropriate energies, an electron from the lower level will absorb it, and it will go to the higher state, and when it cascades down, it will enhance the original recombination spectra. So the spectra from the cloud is going to come out stronger. On the right, it's showing case D, where the same thing is happening with continuum pumping, but just like case B, because it's an optically thick cloud, there are multiple scatterings. So there are these 2 things that's modifying the spectra. So here I have shown a comparison of all 4 cases. On the top, you can see that case C is a lot enhanced compared to case A because of continuum pumping. And here, if you compare case B and case D is a little bit enhanced than case B. That's because it's apart from being enhanced by continuum pumping, it's also getting suppressed because of the multiple scattering. So what I want to mention here was case D was not considered until recently for X-ray because it was thought that case D will be identical with case B, but in our studies, we see that there are some differences that's definitely detectable in microcalorimeters. So yeah, I just want to point your attention to case D because it is the better representation of a nebula if it's optically thick and there is a radiation source. Case D will be the better case to explain the line formation processes. So there are various atomic processes that contributes to the change in the line intensities of the spectra. There is case A or case B transition or C2D transition, depending on whether the cloud is collisionally ionized or photoionized. There is line interlocking and resonant Auger destruction, electron scattering escape, photoelectric absorption, and quaternium pumping. And I'll talk about each of the processes and show you what kind of changes it makes in the spectra. So this plot is showing case A to B transition applied to Perseus cluster. So case A to B transition happens if there is a change in optical depth or there is a change in column density. So here I have plotted iron 25 K alpha lines with respect to their ratios of iron 25 K alpha lines with respect to the brightest resonant line. And so in the case A limit, as you can see that all the lines are kind of going parallel. By the way, the solid lines here are the cloudy estimated line ratios with their errors, and the horizontal blocks there are the Hitomi observed line ratios. So in the lower column density limit, everything is kind of parallel because all the line intensities are increasing with column density. So that's why you don't see any change. But in the higher column density limit, there are some redistribution in the spectrum. So you see this kind of changes here. If you look at the spectra, this is happening basically because Z intensity is going up. And that happens because of case B transition that I have just shown you in the higher level, in the higher Lyman lines. And same for Y. The change in X is mostly due to resonant Auger destruction, which I'll talk about in a little bit. So by comparing this cloudy simulated and Hitomi observed line ratios, we introduce a novel method of measuring column density. Here it only constrains it because X, Y, and Z are still very optically thin at the actual column density of Perseus. So these are the upper limit of the column density from the intersection of the two line ratios that you see. And these dashed lines here are the actual column density reported by Hitomi collaboration. So you can see that they are consistent, but in this case, you can only constrain the column density rather than actually measuring it. If you apply it to a higher column density system, this will be actually very useful in actually measuring column density, which we'll probably do if we have more high column density sources or once we have microcalorimeters with such great quality spectra. So the next process is line interlocking and resonant Auger destruction. So this happens when, in this plot, I have shown the total optical depth versus wavelengths. So as you can see that there are, so these are the iron 25 lines, and there are some iron 24 lines around that, or some chromium line, and then there is iron 23 here. So line interlocking happens if, for example, iron 25 lines is emitted, and there is a iron 23 plus energy level that's sort of equivalent to the line emitted so that it can absorb it, which means the original line will lose its identity and it will be absorbed in a different ion. So this process is called line interlocking. So iron 25 line photon here, mainly X can be absorbed by iron 23 plus, or there are some chromium ions there because of line interlocking. And then if the absorbing ion auto-ionizes, which depends on its auto-ionizing rate, so that will mean that the original photon that was absorbed, it's lost. So which means there will be a deficit in the line intensity of the absorbing of the observed line. So this is what you see in the plot here. It starts out at 1, but then this showing the fraction of the line intensity that's gone because of RAD. And as you can see that if you increase the column density, the intensity decreases, and that's happening because the line intensity is getting smaller because of the resonant Auger destruction. The third process is electron scattering escape, which happens if there are fast thermal electrons in the cloud, which can cause one scattering escape in some of the line photons. This happens if the line photon scatters of these electrons and they get a big Doppler shift and they are shifted from their line center. And because of that, their line profiles will be kind of broadened. And I have shown a cartoon of this process here. This black line is the without ESC case, where you can see that it's sharp and all the photons are there. But this red line is much flatter, which is the with electron scattering case. And this is happening because some of the photons that were here, it got Doppler shifted away from the center and sort of makes the profile flatter. So the high resolution telescopes like Prism and Athena, they will only detect the narrow line component because this broad profile is kind of merged in the continuum and you won't really see it. So the next process is photoelectric absorption. It's a fairly simple process where a photon is absorbed in a system where an electron can absorb the energy of the photon and it can escape or go to a next another energy level. So that can cause deficit in the line intensity if that happens. Just like I explained that if a system is photoionized, there can be continuum pumping that changes the spectrum. So what kind of change you will see in photoionized emission lines in real world? So here I have introduced a line modification factor that gives you the number by which a line is suppressed or enhanced by. The enhancement is happening because of continuum pumping, and the suppression can be happening because of absorption or scattering, the electron scattering or photoelectric absorption, such processes. So you can see that in the left where the column density is smaller, the line modification factor is really big. And then the column density is bigger, the line modification factor approaches 0. And this is kind of how it will transit from in terms of line intensity. At this end, the continuum pumping is dominating, and at this end, the absorption scattering processes are dominating. And in case of photoionized emission lines, the line modification factors can be bigger or smaller than 1. This is how the collisional ionized emission lines will look. Here, the line modification factor cannot be greater than 1 because there is no radiation source there. And as you can see that at the lower column density limit, it approaches 1, and at the bigger column density limit, it's much smaller than 1, approaches 0 eventually. So far I have talked about photoionized system and collisionally ionized systems separately, but the real astronomical sources can be hybrid, which means they can have both photoionization and collisional ionization. This is such an example. This is this is the Chandra HETG spectrum of V1223 HCR. This is an X-ray binary. So I have modeled a spectrum with cloudy, which includes a cooling flow component and a photoionized component, which comes from the diffuse radiation in the cooling flow. So in the plot on the left here, the model perfectly fits the spectrum. And because in this model, this includes all the atomic processes that I have just described. But the plot on the right, I have switched off the continuum pumping and scattering and absorption. So there are some atomic processes missing, and you can see what happens to the fit of the spectra. The model spectra is now missing all these lines between oxygen and magnesium, all the hydrogen and helium-like lines. This is because these lines were photoionized, and because I have switched off the continuum pumping, this you don't see them, they're kind of suppressed. But this line here, the silicon line, this was a collisionally ionized line, so not affected by continuum pumping, but you can see that there is an enhancement there, and that is because if you switch off the processes, the absorption and scattering, this is that's what makes the lines enhanced. So this plot shows why is it important to understand all the atomic processes and include it to your calculation if you want to understand high resolution spectra better. So to summarize, so I have discussed about 4 limits, cases A, B, C, and D to describe the line formation, and showed an application on the Perseus Hitomi observation of Perseus cluster, which can be a novel method of measuring column density using cloudy simulations and observations. And then I described the physics of resonant Auger destruction, with changes in the line intensity. And then I have also shown an application on the Chandra HETG spectrum of a binary system, and showed what kind of difference can it make if you switch off all the atomic processes. So this was what I worked as a part of my dissertation project. So now I am working with the AtomDB group. I'm working with Adam Foster and Randall Smith. So here are some of the projects that I am working on now. So there is a resonance scattering model that I am trying to include in AtomDB that will be that you can import in XSpec. So resonance scattering happens when optically thick photons are absorbed by ions, and they are re-emitted in different directions. And you will see this kind of suppression because of that. And to include the resonance scattering models, there is a 2-step approach that I am taking. First is finding out which lines are important, or which lines have bigger enough optical depth to contribute to resonance scattering, and then how much emissivity changes there will be if the optical depth is that. So there are about some more than 300 lines. I did these simulations for Perseus-like system. So if you compare the red and blue dots, the red dot is without resonance scattering line emissivity, and the blue dot is with resonance scattering. So this is kind of suppressed there. So that's something I'm working on now. And I'm also working on the variable APEC module that lets the line intensities, that lets the user ask the questions that which line intensities and ratios are sensitive to the change in atomic data. So you can vary the atomic data there, like Einstein A or collision strength, or whichever one you want to, by a factor for range of temperature and densities. And then you can ask the questions, are the physical parameters that you get by fitting the data with the model will be sensitive to the uncertainty in the atomic data or not? So an RU student, Rachel Hemmer, she worked with me and Adam Foster on the Hitomi spectrum of Perseus cluster and fitting it with the variable epoch module using the real uncertainty from different databases and including it in it. And this is what we saw. So on the plot here, the run number, this is basically representing, so we created a random distribution of the uncertainties within the uncertainty range that we found comparing different databases, and so that's what the run numbers are. And then we see this distribution in temperature, abundance, and scattering factor. And then the black line is the regular APEC, no change in uncertainty best fit values. And these are the histograms of it. Yeah, so this was the end of my talk. If you have any questions, please feel free to ask.
Thank you so much. Do you have any questions from the in-person audience?
Before anybody asks, we're making the models for XSpec, but they're natively in Python, so they will go into Sherpa immediately. The XSpec requires additional work. But the question I had was, you showed that Cloudy had updated the K alpha wavelengths to better match NIST. But I was surprised that you didn't just change them to be the NIST values. What data set did you use to change the wavelengths?
It was a two-step process. So we first updated the ionization potential there. They're using an old value and stopping it at 4 significant digits that were kind of significantly contributing to the spectra, the discrepancy in the wavelength. And then after we fixed that, we got a polynomial to match it. Still there was some discrepancy, and we fitted a polynomial to match it with the NIST data.
You showed the Hitomi constraints that you derived, and then you said, and the right answer is what the Hitomi team said, which is the dashed line. Why are they right? They are not using a sophisticated set of atomic data as you, so they must be doing. What are they doing?
Yeah, that's a good comment. So they modeled the spectra with APEC to get the column density, and usually like clusters are optically thin. So I guess the right answer will be like to not have a optically thick value, which is like.
Okay, thank you. Any more questions? No. Amy, Anna, can you see any question online?
No questions online.
No question. Okay. So let's thank our speakers today. And see you next week.
Sorry,
Thank you. Sorry about the that's amazing.